Yeah, I think we're close enough. Okay. Well, good afternoon, everyone. Uh, Welcome to the, believe it or not, 32nd annual meeting of the Facet Faithful. Uh, the subject for today is the case for low aspect ratio personal aircraft. And this is something I've been working on for many, many years. I think some of you may remember when I flew the original Facetmobile here in 1994. But the work didn't stop then. I'm continuing the project. I'm continuing developing the concept. And what I want to talk about today is basically, why would you build an airplane that looks like that? So my name's Barnaby Wainfan. For those of you who don't know me, I've been a professional airplane designer for 46 years and an EAA member for 53. At last count, I can count 30 airframes I've worked on that have actually made it into the air. And I'm not done yet. So, we could talk all day on this chart, but that's not really where we're at for this particular presentation. Okay, so what am I really thinking about here? I'm thinking about what is a better personal airplane. And what I mean by that is an airplane that's aimed at private pilots for the way we really fly, not the way the marketing department tries to sell it to us. You know, I still think it's funny. I have a Cessna 150 that I dearly love, but that airplane's official name is the Commuter. How many people actually go to and from work in a Cessna 150? I'd love that gig, but I don't think it's very common. We have one. I think, sir, you're the first one in many years of giving this presentation. So congratulations. I'm jealous. But, you know, it's not an easy thing to do because the conventional wing body, a lot of very smart people, a lot of very good people have been working on the conventional configuration for a very long time. And they've done some very good work. So if you're setting out to do better than a well-established, well-refined configuration, you really need to do some deep thinking about what are we trying to achieve here. And so the first step is to figure out what private pilots really buy. And I found this statistic really interesting. This is old. This is about 10 years old chart. But look at how many more 172s Cessna has sold than Beechcraft has sold Bonanzas. Now, you know, I mean, if you look at the Bonanza, right, if you're just saying someone give me an airplane, most of us will take the Bonanza. But if you're looking for an airplane that fits your budget, and for a lot of us, your honestly assessed pilot skill, even though the 172 is far from a sexy ride, it obviously fits a really valuable place in the market. That's the reason it's been in production so long. That's the reason they made so many of them. So, you know, what's important about that? What does the private pilot really need? Well, the first thing is they're flown by private pilots, not commercial. They don't make money for anyone, right? Most of our flights are relatively short, an hour, maybe two, 100, 200 miles. You know, unless you're making the occasional pilgrimage to Oshkosh or some other, you know, long cross country. But that, you know, that bottom end sport airplane for a private pilot is going to fly average durations in the 1 to 2 hour range. Predominantly VFR, predominantly relatively low altitude, operating out of relatively small airports. I mean, I live in Independence, Oregon. You know, our runway's 3,000 feet. It's not that small, but, you know, I'm not going to fly a jet out of there. And cost is important. I mean, cost is important on any project, but for private pilots, it's doubly important. And the reason for that, of course, is that airplane is you indulging yourself. It's not making you any money. So it has to be bought with discretionary income. So what do I need? I need to be able to afford it. I need it to be safely operable with modest pilot skill, you know, because let's be honest, how many of us fly more than 50 hours even a year? That's a good year for a lot of us. Yeah, well, I know you, but you're always a troublemaker. Yeah, Yeah, that man back there was one of the best pilots I've ever flown with, by the way. But the point is that even when we do go flying, most of the time we're not doing proficiency work. We're going up to Site C. We're going to get the $100 hamburger. And so that means the level of proficiency, particularly from emergency viewpoint, from edge of the envelope viewpoint, it's not all that great. From a designer's viewpoint, what it means essentially is, and I'll probably say this on a later chart, the airplane should protect the pilot because the pilot probably doesn't have the skill to protect the airplane. Good enough performance, what that means is it's got to climb well enough to get over the trees at the end of the runway. It's got to be fast enough for modest cross countries, you know, but I'm not trying to set any speed records. Adequate useful load, and I'll be talking about that a little bit more later because that's a big deal. And a comfortable cockpit environment. Now, you know, for small values of comfortable. You know, but it's interesting because people have over the time gotten bigger. You know, I own a 1975 Cessna 150 Mike, and I love my little airplane, but you know, I have been in that airplane with people who I flew with 30 years ago in another Cessna 150, and we've definitely concluded that the airplane has gotten smaller. So you have to have enough room. Useful load's a big deal. You know, back when most of the two-place airplanes we fly, the old Part 23 certified airplanes, an FAA standard person was 170 pounds. So if you're designing a two-place airplane, you're designing for 340 pounds plus fuel plus baggage. Now, if you look at the actual numbers, look at the, you know, biometric data. Right now in the United States, males 35 to 39, the median weight, which means 50% of the population is heavier than that, is 194 pounds. 75th percentile is 227 pounds. So if I take two people, 75th percentile, plus 25 gallons of fuel, I'm a little over 600 pounds in useful load. So that's kind of an interesting target number, but that's a lot more useful load than most of our legacy two-place airplanes have. And by the way, I think that's one of the things that's wonderful about the regulation changes that just came through with Mosaic. Because if you look at it, that 1320 gross weight for light sport was crippling a lot of otherwise good airplanes to stay legal with any reasonable useful weight. Take the gross weight requirement off, leave the others, and suddenly, yes, I can actually build an airplane to carry that much load. And maybe it weighs 1,400 or 1,500 pounds, but it's still legal and still within the intent of the rule. Okay, I've pretty much said most of this. Now, I think some of us at EAA would, in fact, dispute the contention that personal aircraft are not necessary for day-to-day life. But fundamentally, it's an indulgence, it's a toy, it's a marvelous toy, it's a cool toy, but it doesn't make you money, and so you're buying it with discretionary income, and you have to be able to afford it. So how much, if I'm designing an airplane, I'm trying to market, how much? Well, I came up with a theory, and that was that a good representation of the amount of discretionary income in the economy is a high-end production luxury car. I'm not talking hypercars, I'm talking things like BMWs, you know, Lexus, something like that. Because if you think about it, every bit of money that someone spends for a car like that, over and above the price of a used Toyota Corolla, is indulgence. Because that used Toyota Corolla will do the transportation job just as well as a Mercedes. Maybe not quite as comfortable, but it'll do the job, right? So if the economy can support making many thousands of cars, sometimes millions in that price point, there's some percentage of those people who will decide to bear the shame of driving a 5-year-old Mercedes instead of a 3-year-old Mercedes and use that money to buy the airplane. So I decided I was going to go check this out. I don't have the chart in this presentation anymore, but I found an entire price history of the Cessna 150 at the Cessna Owners Association. What did it cost in then-year dollars, and how many did they sell? Did the same thing for their Cadillac Coupe de Ville. And the correlation was amazing. As long as the airplane cost less than 125% of the Cadillac, Cessna was delivering over 1,000 airplanes a year. As soon as it got to 130%, the bottom fell out. But look at what we were up against. And, you know, this has changed somewhat with light sport and all that, because this is a chart from about 2006. But, you know, when I learned how to fly in 1973, there was a $1,000 difference, a 10% difference between the airplane and the high-end luxury car. Now you roll the clock ahead to 2006, and it's a factor of 2. So it just gives you a rough idea of the target. And frankly, if you look at the pricing of light sport airplanes now, they're tracking this pretty close if you look at the high-end luxury cars. The other thing about flying for fun is you would prefer not to get killed doing it. And so you want to make the airplane safe. So what does that mean? Well, first things first. 2 quotes from history which I love. One from the Royal Air Force, which is, when a crash seems inevitable, endeavor to strike the softest, chiefest object in the vicinity as gently as possible. And the other quote is from Max Stanley, who was a Northrop test pilot who actually put the first flight on this airplane and all of the big flying wings. And that is that the Piper Cub is the safest airplane in the world because it can just barely kill you. Okay, but let's try to look at that at a slightly deeper level. Okay, you know, there's that old saying that takeoffs are optional, landings are mandatory. So once you take off, what are the possible outcomes for a flight? Well, first of all, don't crash. If I get to a normal, safe landing where I intended to land, perfect. That's what I intended to do. If I can make a safe precautionary landing because something doesn't smell right, something doesn't feel right, the weather's closing in, fine, I'm overnighting somewhere I didn't want to be. Life is still good, right? Even if I make a forced landing, if I glide down onto a road, come to a stop intact and unhurt, not the best day in my life, but I'll take it. It gets progressively worse from there, right? So, marginally acceptable, damage the airplane, but not the people. You know, and this is actually an important thing to remember, you know, when we talk about like the impossible turn after an engine failure, because people who are trying to save the airplane when there isn't enough energy to do so very often lose both the airplane and themselves. You know, and then it gets progressively worse from there. You know, survivable crash with injuries, not good, and obviously, worst case, unacceptable. But here's the interesting thing. All of the acceptable ones, up and to and including sacrifice the airplane to save the humans, requires that the pilot be able to maintain control of the airplane until it comes to a full stop. So from a designer's viewpoint, I'm looking at, okay, I need that. Now when we start looking at survivability, this is, for want of a better word, the curve of doom. This is a bunch of crash data correlated between, on the vertical axis is the angle between the flight path and the ground when you arrive at the ground, and on the x-axis is speed. There's a lot of insight in this curve. If you're on the upside of the curve, you're dead. Above the curve, you're dead. Now, if you're below the curve, that doesn't mean you walk away whistling a happy tune, but it means you can at least be dragged from the wreckage in repairable condition. Now, if you take a look at this, there's a lot of interesting stuff here. Because first of all, look over here at 45 knots, 90 degrees. That 45 knot light sport stall speed is not stupid. What it's basically saying is if I can hit at or below 45 knots, unless I fly into a brick wall, my odds of survival are pretty darn good. You look at the Part 23 61 knot stall speed. Well, guess what? That's about a 30-degree impact angle. Okay, so we had a couple of knots, maybe 20 degrees. That is steeper than the best L over D glide into the ground. So what it says is, if I have a 61 knot stall speed, if I lose the engine, maintain control of the airplane, and just glide into the ground, once again, don't fly into a brick wall, I will probably live through it. So this is the interesting thing from the EAA experimental aircraft viewpoint. We are not legally required by the government to meet those regulations, but the physics is the same for us as for somebody flying a Part 23 certified airplane. And here's the other one that gets me. And that is if you look out at the end at about 78 knots. If you're going much faster than that, you make an unscheduled impact with the ground, you're dead. Now that doesn't sound so fast to us airplane people. But remember, 78 knots is a bit over 90 miles an hour. Imagine me putting you in a car, disabling the steering and the brakes, and randomly dropping you on random terrain at 90 to 100 miles an hour. Yeah, that's not going to be a good day. So when you take a look at higher wing loading airplanes, and by the way, the vertical lines are wing loadings in pounds per square foot stall speed with a relatively standard maximum lift coefficient. So what it says is when your wing loading gets much above 30 pounds per square foot, if you do not make it to a smooth runway, you're in deep trouble. Not surprising that we're down in the 20 pounds per square foot and lower, because remember, you're probably going to be approaching 15, 20% faster than this, right? You know, because like FAR 23 says 1.4 V stall for approach. So that whole curve moves that way. So, message here. Hit slow, hit flat. Pilot has to maintain control to do that. Pilot skill, right? Loss of control and stall spin still kills people. And you know, a lot of the high performance airplanes that are out there, certainly the higher performance airplanes, still require a good bit of skill to stay ahead of. And even a good old Cessna 150, if you pull too hard on base, the final will depart and will at best frighten you badly and at worst kill you. From a designer's viewpoint, what you realize is the airplane has to have benign enough characteristics, even in the pattern or anywhere else, that if the pilot screws up a bit, the airplane will whack them upside the head and say, hey, boss, I don't like this, but won't jump out from under them. Right? And, you know, I overheard kind of the last bit of the previous presenter, and they were talking about that impulse to pull when the ground, you know, at low altitude, when the earth fills up with, your windshield fills up with earth, if you stall it. And you want an airplane that isn't just going to completely depart. Okay, well, can we do that by improving conventional airplanes? And the answer is people have tried, and there's been actual real success in some areas. You know, the Ercoupe was certified as characteristically incapable of stalling and spinning. And it really is. Two-place airplane, limited performance, but it really worked up to a point. Ballistic parachutes. You know, the last time I looked, BRS was claiming over 500 lives saved with ballistic parachute deploys. And if you look at the discontinuous leading edge cuffs on the, let's get here. On the Cessna 150 there, that can make, on the 172, that can make an airplane very spin resistant. Icon has, there's a little bit of this, and Cirrus Icon is using a wing design something like this. So yeah, there are some improvements that can be made. There's no question. When we're trying to reduce cost, you know, people have tried all kinds of interesting things with manufacturability. You know, the Republic CB was built on very sophisticated stretch forming machinery left over from World War II. So it had very few ribs, beaded skins, many fewer man hours to put it together. That little airplane on the bottom there is called the Amy Trojan, and it, strangely enough, had external ribs, no ribs on the inside, because it's easier to rivet. Symmetric airfoil wings so that you can change skins left to right and top to bottom, and flat plate tail surfaces. And then NASA actually did a study about 20 years ago with that kind of duck fan thing, with the idea of what if we took CB style manufacturing and brought it into the present day. Now, these techniques did reduce the cost somewhat, but the performance, either there was a performance penalty or it wasn't enough to fundamentally change the equation. Okay. So, improving conventional airplanes only takes us so far. Now what? Well, in the immortal words of Monty Python, now for something completely different. The basic idea here is to address things at the vehicle architecture level, not trying to put better technology and better manufacturing on a conventional airplane. Now, I am not knocking my friend Randy Schlitter at all here. S9's a great airplane, and Randy builds wonderful airplanes. But here's the interesting contrast. The S9 and the Facetmobile both use the same Rotax 503 engine. Facetmobile's faster, lands slower, carries more useful load, and has about half the parts count. So if you look at it, if I'm building this lifting body airplane, about the time I do as much work as it would take to build the fuselage of an S9, I've got an airplane. So manufacturability starts feeding into this equation, but in a different way. And one way to look at this is, the standard design approach is to look at one variable at a time. You lay out a configuration, you figure out how to fit structure in it, how to get payload. So, wing, body, tail. It's a great configuration because you can change any variable without messing with the other ones. That's one of the reasons it's lasted so long. It's a good configuration for an airplane. But what if you start looking at it in a multivariate way where we're thinking of all of it simultaneously? A lot harder, but a lot of potential. And once again, that doesn't need computers either. All it needs is the right kind of mind. And one of the first people who had that right kind of mind, and one of my professional heroes, was Jack Northrop. And if you want to see a truly brilliant technical paper, look up Jack Northrop's 1947 Wilbur Wright lecture to the Royal Aeronautical Society, where he's talking about all-wing airplanes. Amazing paper. The way that man understood things is mind-blowing. But a few quotes. He's talking about, and I quote, a type of airplane in which all the functions of a satisfactory flying machine are disposed and accommodated within the outline of the airfoil itself. In other words, there's nothing extraneous. It's one lifting surface that does it all. And, the YB-49 was essentially Mr. Northrop's final product going for that. But you can generalize the idea beyond the pure flying wing, taking that quote from Mr. Northrop, and say configurations where everything lifts. And the interesting thing is, if you look at this, you can be anywhere from an aspect ratio on the X-24B there of about 0.5, up to the aspect ratio 7 YB-49 with a flying flapjack. And I had the honor of being the flight sciences lead and the aero designer on the X-47B, which is the airplane in the upper right corner. And just to give you an idea of how good you can do with a truly clean, all-wet, all-lifting configuration, that airplane had an aspect ratio of 4.5 and a max L/D of over 19. I used to have a comparison chart that I used to show of this airplane and a Super Hornet with the stores on it, because this airplane complete has less drag than the stores carried on a standard loadout on a Super Hornet. So that's what clean design can do for you. But, and once again, Mr. Northrop understood this. He was building big airplanes, and I'll leave you to read most of what he had to say there. The dimensions of the average human body may also at times be the limiting factor. He was building big bombers. You could put the pilot on a tiny little canopy in the nose. 172-foot span. The problem is people don't scale. You can scale the airplane down, but you can't scale the person down. So at what point can't you make an all-lifting configuration that will fit actual humans? Okay. If I take a normal medium aspect ratio flying wing shape, it just gets too big. Because about the minimum chord, if I say a 20% thick airfoil, and you can get aggressive, maybe you go 25%. To enclose a single upright seated person is about 17.5 feet root chord. So if I'm trying to do a fully blended all lifting configuration, minimum chord is somewhere between 16 and 18 feet. Facetmobile has an 18.5-foot root chord, by the way, just to put it in perspective. So what does that do for me? Well, if I start with the old Northrop plan form and say I'm going to put that 17.5-foot root cord and scale it like it's an N9M or something like that, I end up with an 80-foot span and 900 plus square feet of wing area. That's a bit much for a two-place airplane, right? So what do? I start cutting the wingtips off until I get down to a reasonable wing loading. And by the way, there's a really good paper in, I think, a 1961 Journal of the Royal Aeronautical Society by G.H. Lee, who describes this idea for airliners and he ended up with an airplane, I'll show you the configuration in a little bit, that looked like a Concorde as interpreted by pudgy planes. But fundamentally what you discover is, if you hold that cord and start shrinking it, your optimum is an aspect ratio somewhere between 1.5 and 2.5. Now, Fastmobile was aspect ratio 1 because it was a single place airplane, and even at that, it was a 3 pound per square foot wing loading. So I was actually a little below the optimum. So, okay, low aspect ratio. Well, let's see what other people have done. Remember, good engineers read history. Well, guess what? Some other people have, none of these ideas are original to me. I just took them a little further. So, you know, the Dyke Delta, one of my inspirations, 555 Alphas in the museum. John Dyke flew that airplane several thousand hours. First flew in like 1960, forward carry, 4 people at close to 200 miles an hour on 180 horsepower. Gotta love it, right? The Avro Vulcan, one of my all-time favorite airplanes. During the Falklands War, it flew the longest combat mission ever flown in Earth's atmosphere, and it held that record until the B-2 broke it, flying to Kosovo. And then there was this interesting little thing called the Arup, which was built in the 1930s. And the story of the Arup is wild, because the guy who built it, his name was Cloyd Snyder, was a podiatrist. And the story is that one day he had a felt heel lift, and he threw it toward his bench, and it glided. And he looked at that and said, that would be a good shape for an airplane. And he went and built it. And as a matter of fact, it turned out to be a pretty good shape for an airplane. But that's got to be one of the craziest inspirations for an airplane configuration I've ever seen. And once again, lots of other experimenters have played with it. The Roar 2175, really interesting experiment from the 1960s. Unfortunately, didn't go into production. The one in the middle on the top there, this is a gentleman I dearly love to meet because he's still practicing. His name is David Rowe. He's an Aussie. And he calls his airplanes UFOs, which stands for Useless Flying Object. But he's built like 5 of them. And then a variety of others, all of which actually perform pretty well. So there's something there. But now, you know, we kind of want to say, okay, what are the advantages for this and how does it work? Well, here are the advantages. First of all, a short, thick structure is intrinsically lighter than a long, slender structure. Just to give you an idea, the Fastmobile had a ramp, zero fuel ramp, empty weight of 370 pounds. And 30 pounds of that was the BRS parachute. And it would carry 300 pounds of useful load on 46 horsepower. And a lot of that is the light, empty weight. Simple structure, low parts count, really nice, benign flying qualities. On Fastmobile, I could hold a stick full aft for as long as I cared to, and it would sink at about 1,000 feet per minute. And the aileron still rolled it, and the rudder still yawed it. Now, you can't hold it forever because you're going to get to the ground, but it would recover immediately as soon as you unloaded it. And I did actually, while I was test flying the Fastmobile, just to try to provoke it. Now, I did do this at high altitude. I'm not entirely crazy. But I took it up to about 5,000 feet, and I rolled it into a 60-degree bank turn. And then I just moved the stick all the way back to the stop. And then I took my feet off the rudder pedals and put the stick to the high side. Now, if you do that in your Cessna, life's going to get real exciting real fast. All the airplane did was kind of wallow around a little bit and very sluggishly roll back to wings level. I will tell you that the day the engine quit at 600 feet, knowing that I could make that 90-degree turn without the airplane falling out from under me, was a very warm feeling. We want nice flying qualities because it's no fun to fly an airplane that's unpleasant, right? One of the interesting things with these long chords, because the mean chord of the airplane is 14 feet, it's got an allowable center of gravity range of 15 inches. When I flew it to Oshkosh, you know, it's a two-stroke engine. You can't get two-stroke oil at every airport. So I had 20 pints of two-stroke oil in a rucksack tied on the rear bulkhead, which is 6 feet behind the CG. It's about a pound a pint. So I put 20 pounds in the airplane. Remember, 650-pound gross weight. 6 feet behind the CG. And the only thing I noticed in the change in the flying qualities is the position of my trim lever moved about an inch. That was it. You want good occupant protection. Well, you look at that when you're sitting in the middle of that cage. You're 7 or 8 feet from the edge everywhere. You got lots of crush space in all directions. Once again, very nice when circumstances make you fly through a fence. And finally, you want a roomy cabin. And the nice thing about a blended low aspect ratio shape like that is it's intrinsically there. I could sit in that airplane in the pilot seat and hold my hands straight out to both sides and not actually touch the window. I had to lean over to touch the window. So, lots of nice theory. Let's do the test, right? So, Fastmobile. Now, one of the things, I joined EAA when I was 16 years old. And I got my first issue of Sport Aviation, and I looked at the cover, and I said, the way to do this right is to do something wild and new, appear out of nowhere, knock their socks off, and get that cover. It took me 20 years, but I did it. You know, some of you are old enough to remember that old song, The Cover of the Rolling Stone. This is it. But what were we really trying to do? First of all, and one of the genesis of the project was here at Oshkosh a couple of years before we started building. And I was walking down the flight line one evening, and I came upon the most god-awful airplane I had ever seen. It was a little white biplane. It was kind of lumpy, and it was kind of dirty, and it literally had a canopy of flat pieces of Lexan held together with sheet metal screws. And I'm standing there thinking uncharitable thoughts about this person's airplane. And then I realized, yes, but he flew his airplane to Oshkosh, and mine is still a sketch on a pad. Get to work, right? So I'm very happy to say the last 2 bullets fully achieved. I think we got the Dead Grass Award for 1994. And we did get UFO reports. 2 that come to mind. When I left Oklahoma City on the way here, I had taken off, and about 5 minutes after I took off, the airport manager came on frequency. His name is Rick, and he said, "Hey, Barnaby, you still on frequency?" I said, "Yeah, Rick, I'm here." He said, "We just got a call from someone in town asking us if we knew anything about that weird thing that just flew over." And he said, no, perfectly normal day. The other one that happened was early in the flight test. You know, early in flight test, you orbit over your home airport. Well, my home airport was Chino, California, home of lots of cool airplanes and about 1 million dairy cattle. And a friend of mine told me he witnessed this because I was flying the airplane. He was coming down the airport perimeter road, and I'm flying along. I'm probably doing 60, 70 knots, right? And he was following a pickup truck, and the guy in the driver of the truck was, you know, had his head out the window looking up. Okay. And then I turned, and then he turned, but the road didn't. And he ended up in the ditch with the cattle exhaust. So, but nonetheless, you know, interesting experiment. So let's get this out of the way right away. It is not an imitation of an F-117 because I didn't know about the F-117, because if I had known about the F-117 in my business, I wouldn't have been allowed to build this airplane if I'd been access to it, right? My friend Peter Lurt, when asked about whether we stole the design from Lockheed, said, yes, we did. It's a nose wheel chock for a C5. So, but fundamentally, it was an exercise in simple to manufacture. You don't need any tooling other than being able to cut the copes at the end of the tubes. And, okay. And the thing is, yes, there is a small drag penalty for being faceted. I estimate somewhere between 5% to 10% parasite drag, so somewhere less than 5% total drag at best L over D. A wind tunnel test I would dearly love to do would be to make a facet mobile model and a smooth mobile model with the same planform and really get that increment. So, you know, if you're any professors out there who are looking for a really cool student project and have a wind tunnel, get in touch. But, you know, one of the questions I get asked is, well, doesn't the flow separate? So we actually got a wind tunnel test on this. If you look on the left, that's cruise angle of attack. You look on the right, that's 30 degrees angle of attack, and the flow's still attached. On this particular run, we were testing vortex generators, but it actually didn't need them. Now, if you look very carefully, you can see inside of the fins on the high angle of attack, there's starting to be a very little bit of separation. And I think the real airplane actually did that. I never tufted it, but when I got to high angle of attack, I could hear a sound that sounded like somebody tapping on the fins. So I think I was getting that little bit of separation in there. So, you know, on to Oshkosh. 1994, this is about 10 minutes after I parked the airplane. And so many people asked me, does it fly, that I finally put it was flown here from Chino, California on my prop card. They kept asking, but at least we tried. And then back then they still had the flyby pattern. So on day 2, while I was out flying in the flyby pattern, one of my friends took this picture. And if you look, you can see the perfect planform of the airplane, including the propeller in the dead grass. You know, and so I think I had the title of the weirdest airplane ever flown to Oshkosh until Bert built the Boomerang. And then he won. But what did we actually achieve? This airplane weighed 370 pounds empty. We normally flew it at 620 pounds, but we actually got it up to 740 pound max gross. 50% plus useful load fraction. We'd do 102 knots at 4,000 feet on a Rotex 503. And I didn't have wheel pants on it. So there's probably another 5 knots in it if it had survived long enough for me to really clean it up. But my block speed all the way from Chino here, including pattern time and all that, was 77 knots on a 46 horsepower 2-stroke engine. And like I said, you could hold the stick full back as long as you like. It didn't mush, buff it, never depart. So count that as a success, I think. Well, in about 1995, this was my first shot at a 2-place design. You can see it here in the wind tunnel and the RC model. And although this has since been superseded, I'm bringing it up because I want to share one little bit of wind tunnel data from that test. This is the lift coefficient versus angle of attack. And this shows something really important. Well, the first thing you notice is max lift is at 30 degrees angle of attack. Approach is at somewhere between 10 and 12. Now, when you realize that a conventional airplane has an entire angle of attack range from 0 lift to stall of about 15 degrees, this is amazing, because what it means is I can double the angle of attack from approach, and although it will mush, it will not depart, which means I've got lots of margin for being ham-fisted about it when I turn and when I maneuver. And it's got a flat top lift curve, so even if you keep pulling, it doesn't do much exciting. Then the other thing that's cool about it, this is pitching moment, nose up is up, and you will notice that when I get out around 20 degrees angle of attack, the magenta curve is full aft stick. It breaks stable, which means even if I hold full aft stick, it'll only trim to 25 degrees angle of attack. Remember, max lift is at 30. So I get the same kind of natural angle of attack limiting that a canard gets, which means the pilot does not have the control power to command the airplane beyond max lift, which means he'll always have some lift margin no matter where he puts the stick. Now, if we go back to the curve of doom, you know, if I stall my 152, hit vertical, life is very bad. If I mush into the ground in my low aspect ratio airplane, I'm at 45 knots, actually less. I rescaled this chart because the minimum speed I got on fast moving was about 30. And so in an emergency, like even if you were VFR into IMC, you could go full aft stick, keep the compass from moving with your feet, and mush it all the way to the ground, and you'd survive the impact. So now some years later, NASA sponsored a study to look at using automated manufacturing and composites to build something similar. I won't go into that in any great detail, but the NASA contractor report is public domain. You can download it from my website, which is waynefan.co, by the way. And a lot of the math and the physics that I'm going to talk about for the rest of this talk is also in that report. Okay, it works, but why? Let's get into the physics of it. Okay, so there is a concept called transport efficiency. And the basic idea is that the goal of an airplane is to transport a useful load from point A to point B. What I care about is how much thrust it takes to make it fly that way, how much fuel it burns. I don't care how efficiently I transport the empty weight of the airplane. I care about the payload. So it's payload to drag ratio that is the critical number, not lift to drag ratio. Now this is the aero guys letting the structures guys horn in on their action a little bit. But fundamentally, it creates, when you understand that, it creates a very different optimum. So let's look at the pieces of it, because I promise this is the only actual derivation in the whole presentation. But if you do the math, what you end up with is this really cool number that transport efficiency is just the payload ratio, the useful load fraction, times the lift to drag ratio. So the payload fraction is structures and systems. Lift to drag ratio is aerodynamics. And this one number lets you trade aerodynamic efficiency and structural efficiency off against each other. Now, once again, I did not invent this. This was first, at least the best publication I've seen on this idea is this paper by G.H. Lee. And he was looking at a short-haul airliner. And what was interesting is Handley Page was looking at an airplane that looked a lot like a DC-9, and they designed a flying wing airliner as an alternative with people seated in the wings. And they were most dismayed when they did the analysis on the flying wing airplane, and it didn't show any advantage over the wing body tail airplane. And then Dr. Lee looked at it and he realized, well, of course, most of the wing is empty. So we just digitally started, or mathematically started cutting the wings off. And the transport efficiency got better and better and better, even though the L over D was going down because it was taking so much empty weight out of the airplane. And then he said, okay, but that's kind of ugly. What if I blend it? And this configuration is actually the beginning of Airbus aircraft. They called it the OG Aerobus. Unfortunately, Handley Page Aircraft went out of business before they could build it. But the paper, although it is expressed in a somewhat convoluted and very British style, is really good. And it's the reference is there. It's in the Journal of the Royal Aeronautical Society. So let's start looking at some of those. Remember this transport efficiency. Let's look at the components. Useful load fraction. So I just did some correlation with what's been out there, right? The black curve to the upper left is low aspect ratio all lifting configurations, and there have been a few. Fastmobile in the upper left, 50%. Some of the Dyke Deltas are at 45 or so. And what's interesting is when you get in the wing body tail airplanes, you're all below 40%. Now, nowadays with composites, some people have gotten to 50% with wing body tail, but we can do the same with low aspect ratio if you really want to push it. Okay, so I'm doing a lot better on the payload over gross weight part of the transport efficiency equation. Now let's look at L over D. Well, see, I lied. There's another equation. Important point here is, without going to the math, there's only 4 factors that that affect lift to drag ratio: span efficiency, wetted area, how much skin there is, and the skin friction coefficient, which is essentially a measure of how smooth you are and whether you have laminar flow or not. there's another factor there that I'll show you in a moment. So the first thing is, once again, going back to FMX 5 wind tunnel data, and all lifting configuration, it's almost impossible not to have a nearly elliptic span load. And that means the span efficiencies are very high. So the dots on this are actual wind tunnel data with the min drag route for FMX 5, without the, by the way, without the tip fins, without the winglets. This is just the hull. So that's actual wind tunnel data, and the fared curve is a 0.9 span efficiency polar. Just to put it in perspective, a really good wing body tail airplane is in the 75% range. So what that means is I have less span, but I'm using it more efficiently. And by the way, if I put tip fins on and they act as winglets, I can actually exceed 1. I've tried that on some airplanes. I'm not doing it on my latest because of structural reasons. Here's the other thing, that skin friction coefficient number I told you about. It's a function of Reynolds number. And Reynolds number is a non-dimensional parameter that's proportional to speed and the chord of the wing. Well, a normal light airplane, the wing chord is about 4 feet, 3-4 million Reynolds number. This thing with this long chord has about a 14 to 15 million Reynolds number. And what that means here is that the skin friction coefficient is something like 20% less than on the lower Reynolds number conventional airplane. And this is all turbulent flow. This is not counting on any laminar flow. And what that means is that even though I've got more wetted area, I'm paying less per square foot than in a conventional configuration. And the beautiful thing is those two factors, the high span efficiency and the low skin friction, improve the L over D just enough that the structural weight fraction wins. And even though the L over D is lower than the conventional airplane, the structural weight fraction is enough better that the transport efficiency is actually higher. So I already said that. So let's get into some comparisons. Once again, let's compare the Facet Mobile, which is a pretty low-tech airplane, to another low-tech airplane, the Cessna 150. Okay. Well, if you look at the top curve, it's lift to drag ratio versus airspeed. Facet Mobile is on bottom, 150 is on top. Aero guy says, argument over. L over D is a lot lower, we're done. When you take the useful load fraction into account and look at transport efficiency, out in the range where we're actually cruising, the magenta curve, the Facet Mobile is actually better. So, where I went to was to say, okay, I designed the other airplane before the LSA rules came along. And then years later, when I got a chance to get back to work on it, I said, okay, I'm going to design something to the 1320 gross weight, because guess what? I can use that empty weight to get more useful load. Now, I cheated a little bit because I said, yeah, but I'm going to register mine as an experimental amateur built, so I'm going to design to 1,400 pounds. Thank you, Mosaic. And so this is the configuration of the airplane I'm building now. Call it the Bat Ray. Got about 60 hours of wind tunnel test, flew an RC model. 18% RC model, flew beautifully. One of the things I truly love, I'm an old school modeler. I started out with stick and tissue and rubber power. We flew this with a Pixhawk autopilot, full-time data logging. And one of the really cool things that happened is when we did the wind tunnel test and I analyzed it to find out where the aft CG limit was, where the neutral point was, it was further aft than I expected, which is nice. It means the airplane's more stable than I expected. But I didn't quite believe it. And we checked the model for make sure everything was in the right place and all that. And then I went back to the data I had logged from the RC model and backed out where the neutral point was from the elevator trim curve. And I got exactly the same number I got in the wind tunnel. Now, to an engineer, this is a wonderful thing when you measure the same quantity with two completely different pieces of apparatus that don't talk to each other, and you get the same number that feels like you have found truth. So, yep, there it is flying. And then I was able to get 2 wind tunnel entries at Cal Poly Pomona in their 4-foot wind tunnel. Once again, if you look at the tufts here at 9 degrees angle of attack, the flow's all nicely attached, except you can see there's a little bit of a bow wave around the shroud that's around the sting to hold the balance. So that's an artifact that you have to correct out of the data. We also got a chance to test both conventional tail and the inverted V-tail. I am going to use the inverted V-tail for 3 reasons. Number 1, they brace each other structurally. Number 2, I can bias the rudders for pitch trim instead of deflecting the elevons up. And remember, elevons act like negative flaps. And the third one is it looks too cool not to do. Simple enough. Well, here's now what the lift curve looks like. I learned a little bit in the 20 years since FMX5 and FMX7, right? CL Max is now about 20% better. We couldn't get beyond 35 degrees in the wind tunnel, so I never did find max lift. But you look at it, once again, absolutely flat top lift curve all the way from 20 to 35 degrees. Once again, that means you're going to have extremely benign characteristics at high angle of attack. Pitching moment curve, similar sort of behavior. These curves, I didn't have the rudders biased to trim, so you can see oil control's neutral. It's actually nose down. But once again, the orange curve is full aft stick. You get the nice angle of attack limiting, and once again, you'll notice that you get that same characteristic nose down pitching moment break about 5 degrees before max lift. So this configuration has that same natural angle of attack limiting. Now I'm going to talk about weights a little bit, or the basis of all the estimates. I'm going to be talking performance. So everything I'm telling you is based off of actual test data in one form or another, or statistical analysis of real things. This is not CFD or, parametric weight analysis. So with weight is always a bugaboo because you never get it right. And one of the first rules of airplane design is no airplane ever got lighter spontaneously. Even if you get it lighter than you planned, your customer is going to give you a 5-pound gold brick and say, take this too. Always happens, right? So, fortunately, I was able to get good, detailed weight breakdown on one of the Dyke Deltas, and I was able to therefore increment it. If I take this skin off and put fabric on, if I take this engine off and put this engine on, take the metal prop off, put the composite one on, right? And I did the same thing starting with the real weights on Facet Mobile and just incrementing off of that. And then I also did a statistical analysis of other low aspect ratio airplanes. Now you can see the variability I got in the weight estimates. The most optimistic one was 516 pounds, and the most pessimistic one was 649. So I chose 650 as my nominal design empty weight. And given that the original Facet Mobile only weighed 370 pounds, I think I got a pretty good shot at making it. So that is the empty weight for everything I'm going to show you. Now, I mean, if I really, and this is at the light sport gross weight, if I really get it under 600 pounds, I'll be a really happy man. Because I mean, getting close to 800 pounds useful load in a 120 horse airplane would be mind blowing. I don't believe it's going to happen, but it would be nice. Now, if I look at comparison with existing airplanes, you can see, notice how heavy things like the 152 and the Diamond are compared to the Bat Ray. Look at the empty weight and you can see how the useful loads come along. I'm basically got close to 100 pounds more useful load than any of the comparable airplanes. Because here's why, when you look at weight fractions, this is a stacked bar graph for the Diamond DA-20 and the Bat Ray. And you can see the gray is the empty weight of the airplane and the green is the useful load. So this will really show you visually how much more of what you're carrying with Bat Ray is useful load. So that's the physics of it. So let's go back to the efficiency comparison. Once again, remember, Bat Ray now is right in the heart of that optimum aspect ratio. It's about 2. So I'm not paying the aspect ratio penalty that I did with Facet Mobile to fit it as a single place airplane, right? So guess what? I've now got to the point where my max L over D is actually a good bit better than a 150. But 150 is a low bar. Lovely airplane. I love my 150. It's got lots of rivets. Nobody cared about parasite drag. It was a trainer. But the DA-20 is a slippery composite, all composite airplane. So if you look at it, once again, the aero guy says, well, answer, much higher L over D, we're done, right? But what I really care about is how much power it takes to fly. So now, at gross weight, if you look on the purple curve is the Cessna 150. The green curve, well, the orange curve, I believe, is the DA-20, and the green curve is the Bat Ray, or vice versa. But if you look at it in the cruise area, the power required to fly is almost identical. But remember, the Bat Ray is flying with like 100 to 150 pounds more useful load. So the transport efficiency, once again, comes out a lot better. So even out around 120 knots, even with the lower L over D, I'm carrying more useful load at the same speed for about the same fuel. And oh, by the way, I can approach about 10 knots slower, and it doesn't stall and it doesn't spin. So, but we're not done yet, because remember, if I'm holding payload constant and the empty weight is going down, and I'm holding horsepower constant, then my power to weight is higher, which means the airplane accelerates faster. And if it's flying at about the same power required for level flight, it means it's got more excess power because it's lighter for rate of climb. So this is really cool, right? At gross weight at sea level, the book says the Cessna climbs 700 feet per minute. I have actually occasionally seen 700 feet per minute in my 150. If I don't eat breakfast, then it's a cold day. DA-20, 800, 850 feet per minute. Bat Ray, 1,600. That's kind of nice. Makes the trees go away real quick. Same thing, low wing loading, higher thrust to weight, takeoff. Okay, Bat Ray, at about 400 feet, I rotate, I'm hitting 50, and I'm climbing through 50-foot obstacle about 550 feet from brake release. About at which time the Cessna 150 driver is saying, well, in a little while I should consider rotating. Okay? And because of the extra weight, the DA-20 is rolling even further. So I'm taking off in less than half the distance of the DA-20, hitting my point and climbing at twice the rate. Kind of cool. Same thing, lower wing loading, right? So, book says the Cessna 152 has a stall speed of 43 knots. DA-20 is 44 knots. Bat Ray is 38. That means I can approach about 6 or 7 knots slower. Remember that stopping or taking off distance goes as V squared. So that 6 or 7 knots on touchdown makes a big difference in how short I can land. So, take off quicker, climb better, land shorter. And then this is what I expect for performance. This is my predicted performance now. The numbers along the top are at the 1320 gross weight for the old LSA. So the rate of climb would come down a little bit at 750 useful at 1400. And I'm only quoting the 120 knots because it was designed around an LSA. You actually have to pitch the prop down a little bit to keep it down. I'm estimating a cruise speed of about 125 to 130 knots. At 6,000 feet, 75%, if I ever bother to put wheel pants and landing gear fairings on it. So, looks good enough to build, right? Okay, so this is the whole structure laid out in SolidWorks. And this gives you an idea of what's happening lately. There is a man trapped in the middle of his obsession. We've been doing a lot of the parts on a homemade CNC machine built by a chapter mate of mine named Robert Haynes. So you got to love this. All of the parts come off the machine. All the copes are cut perfectly. The pilot holes are all there. You can Cleco it up with no jigging at all. And it's dead square. Just to give you an idea, when I Clecoed the whole thing up and put it on Sawhorses, took a digital level on all of the cross-ship tubes, and the deviation was less than the calibration of the digital level. It was less than 1/10 of a degree. I think I still have this picture in there also, but if you look at the fit up on the outer panels now come off, the leading edges match perfectly. The trailing edges, I was off by approximately the thickness of the tube. So we were holding 35 thousandths tolerance and 14 feet. That's what NCs can do. And that's really cool. I mean, I didn't invent that, but it's really cool. So this gives you an idea what the overall structure of the airplane looks like. The only difference between these pictures, which were taken a while ago, and now, it looks the same, but most of the clecos have magically turned into rivets. But this gives you an idea of the overall structure. This engine mount is actually an engine mount from an Ariane Lightning, and right now, a friend of mine back home is welding some extra tubes on there to move that upper attach point to an actual hard point on the structure to get the load paths right. One of the things I've been doing along the way, by the way, which is peripheral to the prime subject, but I think it's cool, so I'll share it with you. I'm doing a lot of 3D printing to make tooling and fixturing. So for example, here, I needed, if you look up on the left, I needed a clamp to hold the tubes in the right position in parallel. So I designed one up and printed it. And then, I have a level app on my phone. Great, except, your phone case is a little wobbly, right? So I made this little carriage there that holds the phone repeatably and has both a flat plane and a V-block. And then similarly, I'm doing things like making those spacers to rig the landing gear. The other thing it's really valuable for is if you're designing complex metal parts, it really helps. Oh well, it got away from me here, hang on. It really helps, you see on the right there, really helps to be able to make a plastic fit up, mock up first. I went through like 3 iterations of that, and then we finally made the real metal parts. And amazingly, wrong way. The real metal parts fit perfectly the first time. So it's really valuable. And some of the parts on this airplane, I went through 3 or 4 iterations of plastic, because some other people may be able to think about some of these things in abstraction better than me. But, I can get to a certain point, and then I have to put it in the actual system and actually look at it. And then I look and go, yeah, that should have been a 1/4 inch longer here, and I need to take 10 thousandths off there. But it's much easier to go grow another plastic part than to make another metal part. So right now, I'm in the final stages of putting the landing gear attach in. Yeah, this is the one I wanted to show you. Okay, if you look on the left, that junction is the junction between the leading edge tubes. If you look on the right, that junction is the junction between the trailing edge tubes. We're out by about 30 thousandths of a perfect fit up on the trailing edge. And that's over a length of 14 feet in a clecoed up structure. So, a lot of cool things. I'm touching the airplane every day. It's making progress. One of these days, God willing, it will be here. And with that, I think this combination of low aspect ratio and NC manufacturing could be revolutionary. I hope that we are successful with Bat Ray in demonstrating the potential of it. That's really what I'm about at this point. And I think it would be a great personal airplane. And so with that, thanks for your attention. And if people have questions, I'll try to answer. Well, you've asked questions forever, for years. I'll get back to you. Do I think there'd be a difference? We had to weld all the joints, yes. And it's not a happy one. The problem is that this is aluminum. It's T6, it's heat-treated aluminum. When you weld it, you lose the heat treat. And welded joints in thin aluminum are notoriously fatigue and cracking prone. It's very different than 4130 steel. Because 4130, like we do for our classic Cubs and things like that, is normalized. It's not heat treated. So as long as you cool it gently, you retain the full physicals of the 4130 steel. welding aluminum is a high art, and nobody that I know of uses welded aluminum as a primary airplane structure. They do it in shipbuilding, but not in airplanes. Yes, sir. Say again? Where am I going to mount my angle of attack meter? Not sure. But, you know, I'm probably going to go glass cockpit on this one. For flight test, if I can put a boom with vanes, I'll see if I can. Okay, well, I'll work my way back. You're next. And I haven't forgotten you. Okay. 6061 T6. Oh, all of the tubes are 1.25 inch diameter. The ones on the compression side of the main bulkheads are 049 wall. Everything else is 035. And I ate a slight weight penalty here because a lot of the tubes could have been 1 inch or 1/2 inch, but it makes the junctions a nightmare.
Okay, that's why you selected.
Yeah, so all the same. But here's one of the other interesting things about structures like this. And, you know, from an engineering viewpoint, you have to know what failure mode you worry about. Nothing in here is sized by the tensile strength of the material. The joints are sized by the tear-out strength of the rivet, of the hole, and everything else is sized by Euler buckling. So that helps set the tube diameter and the tube thickness. All right, gentleman in the back.
Do you really need an AOA indicator?
Do I really need an AOA indicator? Well, I probably don't for normal operations, but if I'm going to test this airplane properly, it would be very nice to instrument it enough because I'd really like to document what it can do completely.
Nice gee whiz thing, isn't it?
Well, yeah. Okay. I've let a lot of you guys go first. You had a question.
My question, first of all, very impressive.
Thank you.
But how do you get in and out?
How do you get in and out? Through the floor. Okay, there's a hatch between the rudder pedal and the front of the seat. On this one, there will also be openable windows in case you clean the gear off it and you can get out the top. On the original airplane, the longerons above my head were 30 inches apart, and I had a knife so I could cut my way out through the fabric. Well, I mean, it would be really dumb to land hard, clean the gear off it, be sitting there listening to the hiss of gasoline dropping on the hot exhaust manifold, and be trapped in there by a piece of fabric. On this one, because the canopy frame is right over your head, I'll have openable windows to get out. Yes, ma'am. Yep. Okay, it's really simple. CG tends to be a percentage of mean aerodynamic chord. Conventional airplane has a mean aerodynamic chord of 4 feet. I have a mean aerodynamic chord of 14 feet. Just that simple. But it's kind of cool, particularly since one of the conventional wisdom things about tailless airplanes is they have a very narrow CG range. But that's only because they're higher aspect ratio. And you don't get the tail moves the aft limit aft and the forward limit forward compared to purely the wing. Okay, you can do that with extended chord even more so, if you can deal with the other aerodynamic consequences of being low aspect ratio. Yes, sir.
Will this also be fabric covered?
Yes, it's going to be fabric covered.
What do you expect your zero rate of climb speed?
What do I expect? What?
Zero rate of climb speed.
Zero rate of climb speed. I really don't know because the wind tunnel data doesn't go out that high. In other words, right now at the natural alpha limit, if I held the stick hard back, it would still climb. Might be an interesting experiment. But yeah, you can't get that far backside on the power curve. Partially because of the light wing loading. Yes, sir.
What is this in the fabric?
Jabiru 3300. Okay, and the person behind you. Yeah. Biggest disadvantages, aside from the fact that getting people to take the risk, his question is one of them. How do you get in and out? It's a pain in the ass, right? The other thing that is interesting when you start doing it is you've got all this volume, but it's surrounded by this very spidery structure. So getting hard points to carry concentrated loads takes a lot of doing, and figuring out ways to make a proper door to get cargo in and out of the shape. I haven't worked on it too much here, but I did a study with a friend. We actually submitted a proposal of saying, what if we did this at caravan size to compete with the Caravan. And the numbers were mind-blowing. It looked like we could cut the fuel burn per pound mile in half.
What about visibility on engine out sink rate?
Well, the visibility, it's really nice to have windows in the floor. And I'll probably put synthetic vision in it today's world. Engine out sink rate is, I mean, fine. I'm gliding at L over D of roughly a flaps up Cessna 150 at 50 knots. It's less. Now, if I go full aft stick and let it sink, it's about 1,000 feet per minute, which is a good hefty thump. But, you know, if I'm gliding at minimum sink, it's maybe 300-400 feet a minute. Yes, sir.
The facets are planar surfaces which come together in an edge.
Yes.
There are edges which are perpendicular to the relative wind.
Yes.
Okay. Is there a recommended maximum angle between the planes?
Yes. Actually, very, very good question. Thank you. Because, first of all, it turns out that there is a relationship between the sweep angle of the brake relative to the free stream and how steep a butt line cut brake you can do. If you go look at classical flap effectiveness data, the funny thing is we all do this without realizing it. Every time you deflect the elevator on your Piper Cub, you're taking a flat plate and rotating another flat plate relative to it. So the classical flap effectiveness, plane flap effectiveness curve says the knee of the curve is at 30 degrees. My experiments say sometimes you can get away with 32. And I actually have derived from a bunch of other people's experimental data a curve of sweep angle versus butt line brake angle as kind of the threshold. And I know from one RC model, you go over that threshold, all kinds of bad things happen. So, yeah, it is a very significant factor. Fortunately, it's relatively easy to figure out.
What's the maximum angle you should do? Did you say 30?
30-ish for normal to the flow. Now on a leading edge flap, if it's far forward, you can go as far as 40. By the time you're mid-chord, it's a little less than that. Yes, sir.
Quick question. So when you made, you mentioned the joint
Yep.
you have there, is that designed to be removable or just, if you
Okay.
build this at home, how do you get it to the airport?
It's designed to be, I treat it as a manufacturing brake. So the idea is, yes, it is removable, but it's not intended as a folding wing airplane. So the way I envision it is you would build it in 3 chunks, or, you know, build it as one, disassociate it, makes it much easier to cover too. You know, try covering something that's 18 feet long and 22 feet wide. Try reaching the middle of that with a paint gun on the top, right? You know, you're talking some serious scaffolding. But the intent would be that you get it there, you assemble it, you safety those bolts, you put semi-permanent fabric gap seals on, and then the idea is if you ever have to transport it, you cut those fabric gap seals and disengage it. So it's not a routine on-off kind of thing. Like I said, a manufacturing brake. So I would say taking it apart and putting it together is roughly equivalent to like a Cessna or something like that, or, you know, a non-folding wing airplane if you have to take it. And we'll see how well that works. Yes, sir.
So didn't that NASA study airplane have like a composite panel?
The NASA study airplane was designed around composite panels.
Is that a significant weight penalty in the tube and fabric?
Hard to tell. The real reason this is a tube and fabric airplane is because I'm doing it by myself. I do not have the engineering skill to design a thin skin composite structure safely. I do have the skill to design, with a little help from my friends, to design a tube truss structure. So part of the choices in the airplane that I'm building now is based on my fabrication and engineering capabilities. I would dearly love to do, I think a mix that would be really nice would be a steel or aluminum tube center cage where all the concentrated loads are, and then do the tail cone and the outer panels as the IKEA plane concept of flat panels, you know, put together with potted inserts. I think from manufacturability viewpoint, it would be very good. It would be heavier, but I don't know how much. Time? Okay, is the next speaker here? I don't want to step on your time. Okay, well, let's get this gentleman in.
Regarding
No, actually not. I mean, I admire the man's work, but I don't have a specific citation from his work. You know, my heroes tend more toward people like Jack Northrop. All right, I think we are coming up on time. I don't know whether there's anyone else in here, but I do want to. Okay, sir. So let's yield to the next speaker. Oh, I could go forever, so I'm gonna be polite about it. So, WayneFan.co. Okay, folks, I will be happy to continue to answer questions under the shade of a tree out there. Give me a minute or two to get my stuff and clear, and then if you want to join me back there to continue the conversation, glad to do so. Thank you.